So it's often important or useful to know when a polynomial factors with real roots. So to this end, we have the quadratic formula, basically, which is what Prop 416 is all about. I know you're so impressed that it's taken this long in your mathematical career to get to a proper treatment of the quadratic formula, but such is life. So suppose we've got two real numbers, so that we've got the following monic polynomial with real coefficients. So by monic here, I just mean that the coefficient in front of the x squared, the leading term, is 1. Oh, and I drew my c gigantic. Sorry, didn't mean to do that. Okay, so we've got x squared plus bx plus c, where b and c are real. Then this is going to be, well, it's going to turn out to be x minus lambda 1, x minus lambda 2, and this can always be factored like this over c. It turns out that the lambdas are real if and only if 4c is less than or equal to b squared, which should be familiar to you from the good old quadratic formula, right? And so the rest of the statement of, well, that's basically the statement of the proposition, but I'm just going to engage in terrible form here by sort of half-handedly proving the statement in the middle of the statement itself. So why not? So we've got bx, and then I'm going to complete the square. So I have b over 2 squared minus b over 2 squared plus c. So I've added a grand total of 0 here. So there's nothing wrong with doing that. And then I'm going to split that apart into, so I've got x plus b over 2 quantities squared minus d squared for the appropriate d here. So the idea here is that d squared is c minus b over 2 quantity squared, some real number that comes from just collecting off the, actually here, let me make this purple so that I can match it with this part right here. Okay. And then I've got a difference of squares formula. So I've got x plus b over 2 plus d x plus b over 2 minus d. And then you can see what my lambda 1 and lambda 2 are. It's these guys, right? Okay. So that's more or less how you prove the statement. And then you just notice that it's only in the case when this guy here is positive, when you're subtracting a positive square, that you have this one set up to break down into these guys. And so you want that to be non-negative. And then if you look at this condition right here, then that's exactly the one that's specified by the proposition. Okay, so that's possibly the worst proposition I've proved in this class yet, but don't worry, I'll try and outdo myself sometime soon. Let's see. And so then the last thing we have from this chapter is that if we've got a polynomial over R and it has degree n and it's at least 1, so what does that mean? This part right here means that we're not dealing with a constant polynomial, then P of x can be written as, and so then we have basically a bunch of linear factors and then we have a bunch of quadratic factors, and I just realized I ran out of space. Okay, rewrite this down here. So then we have a bunch of quadratic factors, and you know what, I'm not even going to bother with notation for these. We'll just call these q1x through qmx. And so the QJs have degree 2. Okay, so what that tells you then is that the QJs are all quadratic, and that any polynomial over R can be factored into a product of linear and quadratics, so you don't get stuck with irreducible cubics or irreducible quartics or something like that. But you might have quadratics that you can't break down over R. And I guess I can also say that in this case then the degree of P is going to be K plus 2M, because you get 1 root for each of these linear terms, and then each of these is a quadratic, so there's going to be each one's going to be start over. Each one will contribute 2 to the degree because each one is quadratic. Okay. Period. The end. Game over.